to continue the research about maze and mathematical graphic theory with me. So today we're going to read this article, A Symbolic Analysis of Relay and Switching Circuits. Some of you might wondering, we're talking about the maze. What is circuit's relationship with maze? Well, firstly, I have found an article named A Symbolic Approach to the all pairs shortest path problem, which is related to some of the algorithm applied to maze that we talked before. And I cannot quite understand that article, but that article has kind of strong relationship with this article, and I found that also the current could solve maze in a super quick speed, so I felt like probably we could map the structure of circuit to the maze structure. And thirdly, this article actually analyzes the circuits in a mathematical way. It uses 1 and 0 to denote the relay and switch behaviors. So probably we could look into this article to find some inspiration in solving maze problem in a mathematical way. This is the reason why I choose to read this article today. So basically, this article considers about a mathematical analysis of certain of the properties of such networks will be made. So it is a mathematical analysis of a network that consists of relay contacts and switches, and it will kind of use some kind of mathematical notation and mathematical properties for such networks. So any circuits will be represented by a set of equations, and a calculation will be developed by manipulating these equations. Look into the second part. It is about series parallel two-terminal circuits. So talks about that any circuits between any two terminals must be either open or closed. And let's associate a syllabus XAB, or more simply, X with the terminal A and B. And this variable will be considered as a function of time and will be called the hindrance of the two terminal circuits A and B. The symbol 0 will be used to represent the hindrance of closed circuits, and the symbol 1 to represent the hindrance of an open circuit. So this is notable because I sometimes will get it wrong, but we need to remember that 0 means that the circuit is closed, and 1 means that the circuit is open. We will look into the other calculation before and find this kind of notation is actually meaningful. And the symbol plus will mean that the series connection of the two terminal circuits are added together, and the multiple will mean that the circuits are connected in parallel. These are some kind of figure interpretation. And we need to remember that the hindrance function is a function of time. Also, for this part of the postulates, only the 1b violates the simple algebra because it says 1 plus 1 is 1. And so XAB shows a duality relationship with A and into the postulates. Let's look at some theorems that will be used in later application. It is about some associate laws and distribute laws. And also it could be proved by taking the value 0 and 1 and list them and make a table. Now it defines a new term that the negative of x, it defined to be a variable which is equal to 1 when x equal to 0 and equal to 0 when x is equal to 1. It also has certain properties which is easy to understand. Then it mentions about some calculus of propositions. Basically, it made analogies of such properties beforehand to class theory, and also some properties that related with the negative, and it mentions De Morgan's law that could be applied later, and we will see how the article tried to prove the Morgan's law. So firstly, it mentions a property named 10a. It says the fx1 to xn, it could be right in this form, which is actually equal to, means that when x1 is equal to 1, fx1 to xn is equal to 1 multiple f1 to xn plus 0, because the negative 1 is 0, and then multiple f0 to xn, which will be equal to f1 to xn. And also it could be written in the 10b's form. The 11a and 11b basically says this could be gradually applied to x2 and x3, and then finally it will become what we see in 12a and 12bb. This part is actually super important. This table talks about the interpretation in the calculus of propositions. Then if we want to prove a certain property, we could actually use the true or false table to prove that. And we could see by 12a, f is equal to the sum of products formed by permuting primes under the terms of x1 to xn in all possible ways, and giving each product a coefficient equal to the value of function when the product is 1. So what it says is that if x1 to xn is 1, then the f would be equal to f1. So it's just like what we write in the 10a, but it is written like in format of with extract all the x1 to n to be the coefficient of the function. And what we can do is that we could expand the function by either 10a or 10b, so it could be, then the variable could be appear at least twice. So basically this is what the expansion x1 would be like. And then the generalization of De Morgan's theory could be proved. It gives an example says that the negative of x plus y multiple z plus wx negative, well, could be written as this form. Let's see how this happens. So the negative of this equation could be written as x negative multiple y multiple z plus wx negative prime, and then it could be written as x negative multiple y negative, and then this should be plus z plus z, yeah, added wx negative, and then it could be written as it should be z multiple, yeah, w plus w, which is the same as the right hand side. This is multiple. And then it states some of the other theorems that might be useful. This part might be a typo, but I think what it means that x multiple x plus y is equal to x. So why we're doing this kind of thing? This is because we want to find the circuits requiring the least number of contacts. It is because when we find the least element that it needs, we could kind of simplify the expression in the form which the least number of letters appear, then we could simplify the whole circuits. I'm thinking that maybe we could use such kind of analogy to the maze, because maze has lots of like dead ends, and if we could like simplify the route of the maze to a route that do not include any dead ends, then the shortest path would appear. So then it shows how this circuits could be simplified. We could see that from its picture, this could be written as W plus. Plus means that added, and the multiple means in parallel. So it would be x plus y multiple w negative and plus x plus z and s plus w negative plus z and z negative plus y plus s v. So what it do is that we could do reduction by use with 17b. So what 17b says that when we write a function like this, we could actually write it in the like right hand of the equation. And also so by its intension, if we have a function like x plus f x z, then we probably could write, it's not plus, it's just x and y and z. We could probably write it as x plus f 1. So basically f x negative would be 1, because when it mentions about x, it could be 0. So let's rewrite the previous equation to be something like w. So this is the equation that we want to do. So we could write it into w plus x plus y multiple 1, and then x plus z multiple s plus 1 plus z, and then we could do multiple z negative plus y plus s. Wait, is it? Yeah, s negative v. So from this, we could see that it could be simplified as w plus x plus y, and x plus z multiple anything plus 1 would be equal to 1 in this 0 and 1 calculation. So we could just reduce this part, plus z negative plus y plus s negative v. I'm sorry, I should mean the multiple beforehand. Then we applied 17b. So this 17b, the original 17b is at f. Something like this would be equal to x plus f 0 y z. This is the original 17b. So we could apply that again for y and x and y. Then the equation would be x y z plus 0 plus z, then multiple 0 negative plus s negative v. Yeah. And it could be simplified as this would be equal to 0 no matter what value z takes. So it would be finalized as something like this, which is kind of the same as it mentions here. Then we're looking into some multi-terminal and non-series parallel circuits, which will be considered as a network, consists of like lots of terminals. And then it mentions that it could be denoted as something like xjk. So it says a two n-terminal network M and N will be said to be equivalent with respect to the n-terminals if and only if xjk is equal to yjk, jk equals to 1 to the n, where xjk is a hindrance of n between terminals j and k, and yjk is that for m between the corresponding terminals. Under this definition, the equivalences of the preceding sections were with respect to two terminals. So basically what it says is that we're looking into two n-terminal networks, and if they kind of connected to the two same terminal, then they will be considered as equivalent. This is the star mesh and delta Y transformations, which I think is super interesting and important to study. And especially I felt like this is a star. This is look like star in the graphic series. So I felt like this might be some important parallel here that wait for me to explore. So let's just look at this. So the figure 8 is a delta to Y transformation. You could see this is a delta here, and so the delta, so for this delta graph, the XAB would equal to R, or like there have another parallel connection is S plus T, which could be written as RS plus RT as noted. And then we could write similarly for XBC. So for XBC, it is equal to S multiple R plus T, which will be equal to RS plus ST. And for X AC, it is kind of same. It's a TR plus TS. So we can see that there are kinds of some similarity here. Then when we kind of draw another graph that kinds of have a center point, we could draw them as, so this is X, so this is A, this is B, this is could be right as RS plus RT, and for B and C it has a, oh wait, so because for B and C it have a similar RS part, so we probably should mirror their position. So this should probably be RS, this should be RT, and for B and to connect B and C we need RS and ST, and we kind of check for AC part, there's a TR and TS here. So this is how a delta to Y transformation happens. And then it mentions something that a Y to delta transformation. So this is a Y to delta transformation. It is also not hard to understand. So for the XAB, it is equal to R plus S, which is equal to R plus S, and multiple R plus T plus T plus S, which you could see from here is that from X to from A to B we could go to S to R, or we could go to S, go to T, go back to T, and go to R. And then when we have such kind of parallel stuff, maybe you could draw some kinds of inspiration from its format like this. So we could write as A B, there's a R plus S, and then there's another parallel stuff, is that r plus t, and then another parallel stuff is probably t plus s. And we could have the similar kind of stuff for B and C. So eventually the graph would be something like this. Wait, this is a C, sorry. Wait, I think for this part we should also kind of mirror their position, because they link C differently. So this is how it should look right now. M-point star also have the mesh equivalent with the central junction point eliminated, and this paper claims the process of it is like a simple 3-point tree. So let's see how it happens. So now we assume it is true for m-1, so we want to prove it by mathematical induction, and we want to prove it for m. So suppose we have constructed mesh circuits from the given m-point star. So we have an m-point star, and then we construct a mesh circuit, and each corner of this mesh will be an m-1 point star. This is we could see that easily in this figure, because you could see that this corner of the delta graph, it is r plus s, and it would construct a 2-point, like a two-point star. And since we have assumed the theory is for m-1, we may replace the nth corner by its mesh equivalent. So what we want to show is that this is already true for m-1, like a point star, and we want to show that the nth corner could also be reduced as a corner of the star. So let's see, like this is a delta we have, and this is r plus s, this is r plus t, and this is s plus t. And what it did is that it replaced this corner to be something like this. This is O, this is r, this is s, and then it is still r plus t, s plus t. Yeah. And then we could see that this part could be denoted as this is AB hindrance, could be denoted as R, like R plus S, and then multiple S plus T plus R plus T, which is actually same here. And so by that we could deduce this corner to be something like S multiple R. So then we could actually say that it is equivalent to m minus point star. Function of a non-series parallel network. So this non-series parallel circuit, like something like this, could be written in the form here, and it could be maybe written as something like this. So how could this thing happen? We want to show that this equation is equal to this equation. Let's try. So we could see that this equation could be written as r plus s multiple r plus t, and then multiple u plus r plus s multiple s plus t multiple v. And from here we could use the 3b, the property 3b that we mentioned before, is x plus yz is equal to x plus y multiple x plus z. So we could actually use this property to simplify this term as r plus st, and then multiple u plus s plus rt multiple v. Then we got ru plus stu plus sv plus rtv. So this is the same as what we got here. Yeah. And then this circuit could also be written in a form like this. You could easily see that it kind of lists all the possible way from A to B and then multiple out of them. This equation could also be proved by this property, and probably you could utilize that for kind of practice. And this hindrance is that this method is that we could draw all possible lines that could break the circuits between the points under consideration. So this is RV plus, so this is how you could directly write this, but sometimes it might not be that as simple as you write the way that we presented before.